Hey everybody, Trey here. Welcome back to another video. I was not expecting to do a video today, but here we are. We had a pretty active day across southern Wisconsin yesterday, where they had their first ever tornado recorded in the month of February. It was a pretty stout, significant looking tornado near the towns of Evansville and Edgerton. Here's a screenshot of that tornado. A little bit of a cone, uncondensed cone there with ground circulation. Lots of power flashes associated with that tornado. Here's a little bit of footage, a little bit of a different vantage point of this tornado. Pretty stout little cone there moving across southern Wisconsin, just south of the Madison area. And this was a pretty intense tornado, it looks like. We'll wait and see what the NWS has to say, but they will do their damage survey and likely will find some pretty significant damage, as there was quite a bit of debris lofted on radar. Here's some additional footage of this tornado. Pretty nice looking cone there from this vantage point as well. So all in all, a pretty stout tornado, especially for February, especially in Wisconsin. Again, it's their first tornado recorded in the month of February since records began. So quite the historic, significant event, all from a setup that really did not look to be all that potent. I posted on my social media pages yesterday and today about the many flies in the ointment with this setup and why I was a little bit skeptical of anything robust happening. But as we can see here, there was certainly some robust activity that did happen. So our job in this video is to determine why that happened. We're going to try to keep this one short. There's not a whole lot to say about this setup, but I do have a hunch as to why this storm was able to overcome the more marginal environment and some of those flies in the ointment that did really end up happening and you can see the snow on the ground there in the video. Pretty incredible to see that. But some of those flies in the ointment did end up happening, and so we will take a look at some of those and the overall environment as a whole, and my hunch as to why this storm in particular was able to produce a pretty significant tornado. So without further ado, let's go ahead and get started. Here is the SPC convective outlook from yesterday morning, the 13Z outlook. They had outlined a marginal risk level 1 out of 5 from northern Illinois into southern Wisconsin, and that really didn't change much throughout the day. They really didn't change those outlook lines in the subsequent convective outlook cycles. 2% tornado risk within that marginal, as well as a 5% damaging wind and large hail risk. So a very low-end all hazards threat with this setup. And we did get a few severe reports, mostly hail reports, a couple wind reports, but we did get a few tornado reports as well. Couple tornadoes, I believe 2 different tornadoes occurred from this activity. The first one here was a brief tornado in Putnam County, Illinois. This is a great photo of this tornado from one of my viewers, John H. I want to send a big thanks to him for sending this in to me. Great shot of the first tornado of the day there. Very brief tornado, little cone funnel you see with some scuddy features there underneath. Was a brief, very weak tornado, but a tornado nonetheless. So that was the first tornado of the day. And then we had our subsequent activity in southern Wisconsin, south of the Madison area, which is the tornado that we showed earlier in those earlier videos. Pretty intense tornado there. And that was really the only tornadic activity of the day. So really the marginal risk verified. For all intents and purposes, it was a very isolated, low-end severe threat for the most part, except for this one storm in southern Wisconsin. And you know, if you were to look at this setup on paper, you might think that it would be, we wouldn't really be able to see such a significant tornado from this event. But again, I have a hunch as to why that was the case, and we'll take a look at that here in just a second. All right, let's dive into the meteorology behind this event. As always, we'll start off at 500 millibars, and this will be at 13Z, so 7 a.m. Central Standard Time yesterday morning, February 8th. So the feature of note with this setup was this trough located across the northern plains, kind of a negatively tilted trough. Strong belt of flow had rounded the base of this trough moving into the Great Lakes region. And this would slowly meander east-northeast throughout the day. And this trough would kind of close off and have quite a bit of cold air associated with it at its center. And really out ahead here toward the base of the trough as well. You see the red dashed lines here. Those are our isotherms, lines of equal temperature. And you see the minus 22, minus 24, minus 26 even here across Minnesota, Iowa, Wisconsin, Illinois. So that was going to help really destabilize the atmosphere, despite very limited low-level moisture advection, or at least very limited low-level moisture as a whole. We'll talk about that in just a second. And that was really one of my major drawbacks to this setup, was the lack of moisture. But it was expected that this very cold air aloft would steepen those lapse rates aloft and help to destabilize the atmosphere, even though we had limited low-level moisture. Let's go down to the surface. Very tight surface low in place to start the day across eastern South Dakota. Strong cyclogenesis had started to occur across the central high plains yesterday and had continued into the day today and to this point where we had a surface low up there in eastern South Dakota to start the day. That surface low would move off to the northeast throughout the day, and by 22Z, 4 p.m. Central Standard Time, that surface low was centered way up here in Minnesota. If we were to draw in our fronts, it would look something like this. Cold front through this pressure tongue here, eastward moving cold front. Warm front, looks like our wind shift is somewhere up here. So our warm front somewhere in that position, maybe a little bit of occlusion going on with this surface low where the cold front actually overtakes the warm front, but at this resolution, a little bit hard to say. But there was a lot of talk on social media whether or not this was a true cold core tornado setup. And the answer is it really was not. Even though we had a 500 millibar closed low that had very cold air at its center, which by definition is a cold core low. You can see here at 22Z, we have a closed contour here at the center of the trough, very cold air associated with the center of that trough. That is, by definition, a cold core 500 millibar low. So we did have a cold core upper low in place, and we also had a surface low in close proximity to that upper low. So there is our surface low, again at 22Z, our upper trough centered somewhere up in here. So we have an upper trough, cold core, upper low, centered very close to the surface low center. And that is a pretty classic hallmark of cold core setups, as the work done by Davies and Guyer has shown. This is Davies and Guyer 2004. These are examples of setups where that have an increased likelihood of cold core tornadoes. You can see the 500 millibar low in very close proximity, usually about 200 statute miles or less from each other. At least that, or between the 500 millibar low and the boundary intersection. Usually we have some sort of boundary intersection between, whether it's between a cold front and a warm front, or a cold front, dry line, and warm front, something like that. But usually there is a boundary intersection just near or ahead of the surface low, and that is a favored location for tornadoes in these cold core type setups. And that was the big difference here. If we go back to our surface map, so here, our upper low centered somewhere in here, surface low right in here, our cold front draped down like this through the pressure tongue, and our warm front somewhere like this. So our boundary intersection is way up here in Minnesota. The surface low and that boundary intersection way up there in Minnesota. Our area of interest was down in here, southern Wisconsin into northern Illinois. Basically out in the open warm sector ahead of this eastward moving cold front, not associated with any boundary intersection. So that was the big difference in making this really not a true cold core tornado setup, is that we did not have the area of interest along a boundary intersection near the main surface low, even though we did have that upper low, the 500 millibar low, that was a closed low and had lots of cold air aloft. So by definition, it was a cold core low, but the overall configuration of the surface low, of the low centers and the area of interest was not did not jive with the work done by Davies and Guyer. And so this was not really a true cold core setup. This was more of just a sort of warm sector, cold front type setup where the storms formed ahead of the eastward moving cold front and had the warm sector to take advantage of. If we had maybe a day more of moisture advection here so that we could get moisture up onto the boundary intersection here in Minnesota, then we'd be talking about number one, a pretty classic cold core type setup, and number two, probably a more robust setup with a lot more interesting activity, because we would have better moisture up here on the actual boundary intersection and surface level. That was not the case with this setup. Our area of interest was well to the southeast of any boundary intersection and the surface low center. So this was, all in all, not a true cold core tornado type setup. Moving on to our surface data, and this was really my biggest skepticism with this event, was getting adequate moisture into the risk area. You can see here that we're starting off at 13Z, 7 a.m. Central Standard Time yesterday morning. And you can see our dew points across the risk area, southern Wisconsin, northern Illinois, in the low to mid 30s across the area. That just really is not going to get the job done. Our 50s dew points relegated way down to the southwest across northwest Oklahoma. And it looked really like we were going to have to get dew points into the upper 40s to maybe low 50s across the risk area to support robust convection, especially with a tornado threat. And that just did not look like it was going to happen. Going back to the day before the event, so the evening of February 7th, this is at 6 p.m. Central Standard Time on the 7th, our 50s dew points were still way down here in East Texas. So it was going to take a gargantuan effort to get that all the way up into the upper Midwest states, and I just didn't think it was going to happen. Now, we did have a robust surface low, as we saw, that was helping to increase and back those winds across the plains to really try to pump that moisture into the Midwest states, but I just didn't think it was going to get the job done with the northeastward track of the surface low up into Minnesota, away from this region. And the fact that the moisture was just way down to the south, it just seemed like it was going to take a really Herculean effort to get that moisture up into the region. Now, we ended up doing all right. As we go to our surface data from yesterday, you can see that we do moisten pretty well throughout the day. As we go into the afternoon hours, we get those 40s dew points up into northern Illinois, even some 50s readings up in there. But here we are at 23Z, about tornado time. Dew points across northern Illinois in the upper 40s, 45 to 48, 49 or so, a couple of 50 readings in there. So not bad moistening across the southern portion of the risk area. But up in Wisconsin, we were still hanging out in the mid 40s at best. Madison 53 over 44, Janesville 57 over 45. So on paper, that really just didn't seem like it was going to support robust tornadic convection. Very cool surface temperatures, very limited low-level moisture. So it just didn't seem like the storms, as they moved into southern Wisconsin, were really going to do anything robust. Maybe some marginal hail, but with this kind of surface profile, it seemed like the thermodynamics as a whole were going to be pretty marginal at best, very much on the weak side. Perhaps with a low-level inversion that those storms would have to deal with, which might negate the tornadic activity up here, but that's not what happened. I can see it definitely a little bit more down here to the south, where temperatures were up into the upper 50s, low 60s, dew points approaching 50 there. That was, about the realm of what I expected to happen, and basically the event was going as expected, with a few storms, a couple hail reports here and there, maybe that brief tornado as we saw in Putnam County, but that was about it. And that was pretty much what you're going to get with this kind of low-level thermodynamic profile. But up here in Wisconsin, just did not seem at the time of the tornado to be all that conducive. But here is where the radar comes in to help us decipher this mystery. So this is some reflectivity data from the KMKX radar, the Milwaukee radar, located right here. Madison is right here, and the Evansville-Edgerton corridor is right in here. So this reflectivity begins at 22:33Z, so 4:33 p.m., about an hour or so before tornado genesis with the Evansville supercell. And you'll notice here right off the bat that there's not really much going on with these storms as they move into southern Wisconsin. Really, they look kind of garbagey, if you will, just a lot of updrafts pockmarked across the radar screen here. Not much organization to these storms. Now, before we go on, I want to note that this environment was pretty strongly sheared. If you go back to our surface map, our surface winds were pretty strong, about 10 to 20 knots or so out of the south. We go up to 850 millibars associated with the low-level cyclone. We had low-level flow, pretty strong low-level jet across the region out of the southwest ahead of the cyclone, basically about 40, 45 knots or so out of the southwest. So very strong veering and strengthening of the low-level winds with height. And we had strong deep layer shear as well, as those winds would continue to strengthen as we went up in the atmosphere at 500 millibars. Those winds were out of the southwest at 80 plus knots or so. So very strong deep layer and low-level shear in this environment. And that's one thing that's very much different than typical cold core type setups. With typical cold core tornado setups, you're much closer to the center of the upper closed low. So your deep layer shear tends to decrease, and that helps, kind of means that the event is more fueled by the thermodynamics rather than the kinematics. Well, in this case, we were far enough removed from the center of that closed 500 millibar low that we were able to interact with the strong belt of flow that was rounding the base of this trough. So you were able to really increase that deep layer and low-level shear in this environment, which made it a little bit different than typical cold core type tornado setups. Now, we've talked about this a lot here with southeast setups before, in that when you have a very strongly sheared environment, if you have isolated updrafts, they're going to really struggle in that strong shear unless they have companions to help them kind of resist that shear to allow them to mature effectively. So again, if you have more isolated type updrafts in a strongly sheared environment, those are going to struggle. But when you start to allow them to cluster together a little bit, they have some companions to kind of resist that getting torn apart by that shear so they can mature. That's when you start to see one or two dominant supercells come together, and then you have your significant tornadoes and you're off to the races. The same thing happened with yesterday's event. So we start off this loop, not much is happening with this convection, not much organization at all. But keep your eye on these southernmost storms here. Number one, this lead supercell, and number two, this kind of clustery looking storm complex back to the west. Now, as the lead supercell moves off to the northeast, it doesn't really do much. It tries to develop a hail core, tries to develop a little bit better supercell shape. It really struggles for the most part until it interacts with the storms back to the west. At that point, once the interaction is underway, it starts to take on a much more supercellular look, starts to develop a much more noticeable hook echo. And at this point, this is when we start to see tornadogenesis occur. You can clearly see it on velocity here. Not much going on at all for quite a while. As that supercell moves north, not much going on, and then eventually it starts to interact with the storms behind it. That is when the velocity couplet starts to increase, and then we have a significant, likely significant tornado once the supercell, the lead supercell, interacts with the storms behind it. So again, this was the interaction of these storms. This was key in helping this supercell produce a likely significant tornado. Once again, very strong shear in the environment. So once it was back here, very isolated, it was struggling to intensify amid that very strong shear. Even though we know that strong shear is very good for producing tornadic supercells, it's not so good when you have more isolated updrafts, as they struggle to not be shredded to pieces in this environment. But once that it starts to interact with the storms behind it, it provides somewhat of a cocoon and allows the lead supercell to do its thing and start producing tornadoes. We eventually get almost a full merger here as well. The lead supercell merges with that portion of the line behind it. We get almost one full supercell here. You can see that merger. The reflectivity really starts to spike in there, probably some large hail, even though, as we know, as we've talked about before, strong low-level shear doesn't really jive with large hail production, but mergers can help offset that. Even though you might have strong low-level shear, you can have storm mergers. That adds a lot of mass to those storms, and that can allow for large hail production, even in the face of strong low-level shear. So we almost get a full merger here, but at the very least, this lead supercell was being shielded, quote unquote, by the cluster of storms to the southwest and west, and that helped it resist that strong shear and start to become dominant and start producing tornadoes. Now, this concept of clustering aiding in the intensification of these storms is also good in drier environments like we had here. Remember, at the time of the tornado, Janesville, just to the southeast of the tornado, was 57/45. So very cool surface temperatures, very limited low-level moisture, which led to likely very weak thermodynamics as a whole. We're going to take a look at some proximity soundings here in just a second. But this concept of clustering helps to overcome this kind of weak moisture environment. Because back here, as you can imagine, as the storm is more isolated, it's sucking in that dry air from the environment, perhaps subject to some dry air entrainment aloft. But as it interacts with the cells behind it, those cells behind it start to moisten the near-storm environment for the lead cell, and that helps to compensate a little bit for the overall marginal thermodynamics weak moisture in the environment. So this storm interaction was absolutely key, in my mind, to helping this supercell produce a likely significant tornado, even though the environment around it did not really suggest tornadoes at all, let alone significant tornadoes. This storm merger and storm interaction was absolutely key. And there's going to be a lot more research coming on this in the next few months, so stay tuned for that. But just know for now that this is a very favorable orientation and configuration for this lead supercell to produce tornadoes. This lead supercell, when it has feeder cells like this in the back to help it along in the ways that we've just discussed, that can help the lead supercell really start producing tornadoes. And we've seen it in many cases before. Again, lots of research coming out on this in the next few months, so stay tuned for that. But this was a very key. This storm interaction was very, very key in helping this supercell overcome the weak environment around it and start producing significant tornadoes. Speaking of the more marginal environment, here is a RAP model proximity sounding at Madison, Wisconsin, so just north of the tornadic supercell at 23Z, so about 30-40 minutes or so before the tornado began. And right away you can see the unimpressive thermodynamics in this environment. 56/47 at the surface as progged by the model. We saw at Janesville observed 57/45, so maybe slightly warmer, slightly drier in the vicinity of that supercell. But overall, this gives us a decent picture of the very marginal thermodynamics. You can see that little kind of kink in the temperature and dew point contours here, leading to very limited low-level instability and deep layer instability as well, only reaching about 350 joules per kilogram of mixed layer CAPE. Despite very cold temperatures aloft, very steep lapse rates, we can see our 500 millibar temperature is about minus 25 or so, 25 degrees Celsius or so. So that is very cold air aloft, and that tried to compensate for the weak low-level thermodynamics, but it really just couldn't get the job done. But as we talked about, the storm interactions, that's why they were so key in overcoming this weak thermodynamic profile. You really needed those to help give that storm a cocoon of a little bit better environment for it to do its thing there. Now the wind profile, much different story. Very impressive looking wind profile here. Very impressive curvature in the low levels of this photograph, strong veering and strengthening of the winds with height, about 10 knots out of the southeast at the surface to about 45 knots or so out of the south-southwest at about a kilometer off the surface. So very strong veering and strengthening of the winds with height, leading to impressive curvature in the low levels of this photograph. So again, if we had had maybe a day more of moisture return up into this region, we'd be talking about a much more significant event. If we had maybe 50s, mid to upper 50s dew points, we'd be talking about a very significant event with this kind of a wind profile. Long photographs as well, bulk shear, effective bulk shear at about 40 knots or so, strong low-level shear once again, approaching 400 meters squared per second squared, so very strong low-level and deep layer shear to support supercells in this environment. But again, the very minimal thermodynamics kept those storms at bay for quite a while until those interactions could take place. Strong streamwise vorticity in the low levels as well, almost purely streamwise vorticity near the surface. Again, streamwise vorticity is when we compare our storm relative wind vector, drawn from our storm motion, to the low levels of the photograph, and our horizontal vorticity vector, which is perpendicular and to the left of the photograph. If those two vectors are parallel to each other, you have streamwise vorticity, which is much more favorable for tornadogenesis, for aiding in tornadogenesis in supercells, as that spin in the environment can just be tilted and stretched into the vertical, and the storm can start the tornadogenesis process, as opposed to crosswise vorticity, where a lot more stuff has to happen to get the tornadic processes underway. But you can see here, up through the lowest levels of the atmosphere, those vectors are pretty much parallel going up through the lowest kilometer or so, so ample streamwise vorticity for any supercell to work with. And again, if you have streamwise vorticity in the environment, but you can't get supercells, it's not going to matter. But we were able to get that supercell to perk up a little bit once those interactions happened. It was able to take advantage of the almost purely streamwise vorticity in the lowest kilometer or so of the atmosphere, and it was off to the races. So overall, very impressive wind profile, very unlike this kind of a setup. Of course, it did have some cold core characteristics and having very marginal thermodynamics, but overall, this wind profile, very uncharacteristic of cold core type setups where you have strong deep layer shear as well as strong low level shear. One other quick note on the radar data from this tornado. This tornado was lofting a lot of debris very high in the atmosphere. This is a 3D look at the correlation coefficient product on radar. The correlation coefficient, if you recall, tells us how correlated the objects are that the radar beam is bouncing off of. So, for example, if the radar beam sees all similarly sized raindrops, the correlation coefficient is going to be near 1. All those particles are basically the same. But if it starts decreasing, especially in proximity, very on top of a tornado vortex signature or velocity couplet, then you know that the radar beam is seeing some different particles in there. So perhaps rain, parts of houses, boards, bricks, nails, tree leaves, etc. And that is why we can use correlation coefficient to tell us if a tornado is in progress, because we can see debris lofted by that tornado. Now this is a 3D look at the correlation coefficient, so we can see how high that debris is being lofted. So here is our debris signature at the surface, and you can see the greens, yellows, and blues here extending all the way up above 20,000 feet in the atmosphere. You can see the green particles here exceeding 20,000 feet in altitude. That is very, very high. That is usually reserved for stronger tornadoes. Now, the research shows that this may be EF2 to EF3. I don't like using the correlation coefficient alone to rate a tornado. That is definitely for the NWS to do for their on-foot ground damage surveys. So we'll leave that to them, but some research has stated that the debris being lofted this high does correlate with a significant tornado, possibly an EF2, low-end EF3 type tornado. But nonetheless, in any case, this tornado was lofting lots of debris very high in the atmosphere, which means lots of strong vertical motion in that tornado. And so that means usually a pretty strong tornado to loft debris over 20,000 feet into the atmosphere. So pretty impressive radar data associated with this tornado. So all in all, it was definitely the storm interactions that made this setup tick. We had a wind profile that was certainly favorable for tornadic supercells, but the thermodynamics overall were going to hold this setup back, except where we had storm interactions. That storm interaction was absolutely key in getting this supercell to produce a tornado. And if it was going to produce a tornado in that kind of a wind profile, strong tornadoes were certainly on the table, although, the thermodynamics were really screaming at us that that was not going to take place. But all it takes is one favorable storm interaction, and again, lots of research coming on that in the near future, so stay tuned for that. But very interesting setup, no question, and it's one that is historic, as it is the first tornado in Wisconsin history, and it was a strong one at that. Very unusual sight for February, but it just shows that you really have to pay attention to the details, and sometimes you're not going to see these kinds of things ahead of time. You're going to have to wait until the storms are in progress to see how they interact, to know if you're going to get any notable tornadic activity or not. So with that, thanks for watching, and we'll see you in the next video.